Hello, ladies and gentlemen. Oh, hi, RJ. Straight in there on the chat. Welcome. So, in this session is the third session of three, essentially this week for year 12 and obviously year 13s as well, because all this stuff's going to be in your exams because these are the three most common. I'll just turn myself off. I can hear myself. Three most common year 12 topics to appear in A-level papers. Now, this is the top one, the absolute top of the shop, because it's always going to be in there somewhere, okay? They love referencing bonding because it's mad as well because students tend to forget this bit, okay? You don't really use it in anything that you're doing in year 13 when you go into there. So it's easy to kind of forget that stuff. And bonding, there's a lot of key terms, there's a lot of things to remember, and you kind of get out of touch with how to answer those questions. And that's what we're going to be focusing on tonight, is how to answer questions. So remember, this is exam training, just like next week, just like May half term. This is what I'm doing, exam training. So it's about obviously remembering things. There's a lot of recall bits in here, like shapes and bond angles and, you know, statements about what metallic bonding is and so on and so forth. But when they present questions to you, how do you answer them? How do you get all the marks? What are they actually looking for? And it's surprisingly easy. It's surprisingly easy to actually hack these questions, okay? And I'm going to show you exactly how and why as we go through this session. So, where do we start? Well, let's start with bonding types. Hey, Cloudy. You've been around today. Excuse the pun. Yeah. Got absolutely soaked walking the dog today, but there we go. Hopefully you're not feeling that way. Hello again, RJ. Hello again, RJ. Where are we starting? Well, let's start with bonding types, okay? Now, in any question, and I want you to kind of write this down, actually, if you've got a pad and paper handy. Bonding strengths and melting points and boiling points and stuff like that, it's all relative, okay? Which is stronger than another? Most questions revolve around that, okay? Knowing that this type of bonding is stronger than that type of bonding and so on and so forth, okay? And making those statements, it's all just relative. There's no quantitative values here, okay? There's no calculations involved with bonding. It's just a case of knowing that is stronger than that, so that has got a higher melting point than that, or a boiling point, or whatever it is, okay? So let's just take a look at this, okay? Oh, don't need that. And I've got this for you to download as usual. So I will just share my screen first and foremost so you can see what it is. And then we are going to paste it in the chat. Boom, there it is, okay? So this here is something I created just over the last couple of days. I'm always trying to explain this kind of like, you know, just in words and stuff like that. I thought, you know what, I'm going to actually put it down on paper. So here are all your major types of bonding, okay, down the left-hand side. So these ones down the left, let's use a pen that stands out here. We've got giant, covalent, ionic, and metallic. These are all your crystal structures, okay? OCR people, they love you to talk about these being crystal structures. And that is a fact, to be fair, but not so important for the other exam boards. But these are your like big things, okay? Then, of course, you've got simple covalent molecules. These are individual molecules like water and methane and carbon dioxide and nitrogen and so on and so forth, okay? Now, these are in descending order of strength, generally speaking. Now, we should know by now, year 12 and 13 chemistry students, that there are lots of rules and patterns in chemistry, but there are also always exceptions. So this is a general overview of the relative strengths of these different types of substance. So, giant, covalent, ionic, metallic, simple covalent at the bottom down here. But of course, when you've got simple covalent molecules, when it comes to melting points and boiling points, these are covalent, and these covalent bonds in here, so let's say you've got CH4 like so, those covalent bonds are really no less strong than the giant covalent bonds we see between carbon atoms in diamond. The difference is that up here we need to break those bonds in order to melt or boil something, and that takes a lot of energy, whereas down here it's all down to intermolecular forces. We are not breaking those bonds. So for example, this is the one I always use, if you take water, liquid water for example, and you boil it, what's the formula for gaseous water? What's the formula for steam? Well, it's still H2O, okay? If you freeze it and you get solid water, what's the formula? It's H2O, and that's a solid. So this just proves, obviously, we're not breaking covalent bonds. We are just separating molecules out from another, okay, from one another. Another analogy I use for these down at the bottom here compared to giant covalent is you think of giant covalent like a massive bowling ball, okay? So if you wanted to break a bowling ball, that takes a lot of energy, okay? So it's really, really hard. It's going to be really, really tough to break those bonds inside a giant covalent molecule. Whereas simple covalent molecules, I mean, I'm sure they might be slightly different, but essentially like snooker balls or pool balls are made of the same stuff. They feel like a tiny bowling ball, right? So in order to melt or boil those, you don't have to break them. You just have to separate them out one from another. So it's like breaking off in a game of pool. It's really easy to separate those pool balls from one another, okay, compared to trying to break a bowling ball down the middle. If you wanted to try and break one of these small molecules up, okay, and break those covalent bonds, it would take a lot of energy. But in order to melt or boil them, we don't have to do that, okay? We just separate them out one from another. So that's my analogy there that I always use in terms of linking, because they're both covalent. Why are they so different in melting and boiling points? That's the difference, okay? Does that make sense, guys, in the chat? Obviously, I go off on a tangent, off-piste sometimes. Does that analogy make sense to you guys? Beautiful. Okay. Thank you. Thank you, Cloudy. So, obviously, we've got hydrogen bonding, permanent dipole, and induced dipole. This causes probably the most stress and anxiety in students when it comes to answering questions as to identifying, and we're going to get into that, okay? So, top of the shop, let's just do some highlighting. Thank you, Scarlett. So, giant covalent, typical examples, diamond, graphite, silicon dioxide, okay, in other words, sand. So as it says, covalent bonds must be broken in order to melt or boil. These require huge amounts of energy, which is why carbon, for example, has the highest melting point of any substance known. I don't know when. Maybe they've developed one now that's higher, but certainly in the natural world, okay? 3,500 degrees or something like that. Then you get your ionic substances. Now, these are kind of much of a muchness, okay? They're just all really, really high because obviously we need to break covalent bonds. When it comes to ionic substances, there are almost limitless combinations of ionic substances we can make. Metal and non-metal, big differences in electronegativity. So sodium chloride, magnesium bromide, potassium iodide, the list goes on, okay? So within this ionic box here, we have got a huge range of melting points and boiling points. What does that actually depend on? Okay, so if we were to compare two ionic substances and they asked us why their melting points are different, what do we need to talk about? So the range within this ionic sphere, if you like, depends on, number one, the charge on the ions. Now, if you've got a 1 plus and a 1 minus, the attraction between those is going to be weaker than between a 2 plus and a 1 minus, for example, okay? So the greater the charge, the stronger the electrostatic attractions. That's a really key phrase there, okay? So the greater the charge, the stronger the attractions. Therefore, you'd expect the melting and boiling point to be higher for that substance compared to another. So for example, if we had sodium chloride and magnesium bromide, and this is why I use them as an example, we've got a 1 plus and a 1 minus. We've got a 2 plus and a 1 minus, okay? I know there's 2 bromines there, but essentially this should, as far as we're concerned, have a higher melting and boiling point because there's one ion in there that's got a greater charge than in sodium chloride, okay? So charge on the ions is very important. Nextly, I mean, I've just made a word up there, haven't I? Let's be honest. Next, ionic radius. Now, again, it's general, and you can rely on this. The smaller the ions, the stronger the electrostatic attractions. So if we've got like lithium and sodium, okay, Li plus and Na plus, because lithium's obviously higher up in the group, it's a smaller ion compared to sodium. So between lithium chloride and sodium chloride, I would say that because lithium is smaller than sodium, then that would have a stronger electrostatic attraction with the chlorine than the sodium would. Okay, so don't worry. They will only ever give you questions comparing ionic substances, A, where the charge is different, but they're in the same period. So they got the same about ionic radius, or the difference will be ionic radius. Okay, so if you look at these, look at two substances like lithium chloride and sodium chloride, you're like, well, the first thing, check for the differences in charge. If the charges are the same, then look for a difference in ionic radius, and the smaller one is always stronger in terms of electrostatic attraction. Hey RJ, we are absolutely getting to that. I've just seen your question. How do you even distinguish what molecule's simple covalent, whether it includes H bonds, dipole, or induced dipole? Well, all those molecules, all simple covalent molecules, have intermolecular forces, and you need to decide whether it's hydrogen, permanent, or induced dipole. Okay, and we're going to get to that. I promise you that. So that's ionic, okay? And even actually what you might find is some ionic substances have lower melting and boiling points than some metals. So there is an overlap here, okay? So they will kind of overlap and metals overlap with them. So like I said, this isn't perfect, it's generalized, but generally speaking, ionic substances do have greater melting and boiling points than metallic substances, okay? But those are the things to look out for. And use these terms wherever. Anywhere in chemistry where you've got something positive attracted to something negative, which happens all over the place, that's an electrostatic attraction, but we tend to use that word when describing ionic bonding, okay? So, metallic bonding. For example, sodium, magnesium, copper, of course. Now, how do we depend on those? How do we look at those ranges? Again, because we've got a massive range of melting and boiling points for metals. So we're just looking at pure metals here from our periodic table. We're not talking about alloys or anything because that's not in the spec. We don't need to know about that in terms of melting and boiling points. But what affects the melting and boiling points of metals? Well, again, it's exactly the same as in ions, okay, as in ionic substances. So the range depends on the charge on the ions. So if you were to take sodium and compare it to magnesium, this is only 1 plus, okay, and I've got obviously a sea of delocalized electrons around it. This is 2 plus, so the electrons are going to have a stronger electrostatic attraction to the metal that's got a more positive charge. Plus the fact it's lost more electrons. You've got a greater number of delocalized electrons where you have ions with greater charges because they've lost more electrons to get there, okay? So that makes sense. The other thing again is ionic radius, okay? So if you've got, for example, Li plus metal surrounded by delocalized electrons, and again, Na plus metal surrounded by delocalized electrons, this is smaller. So it's going to have a higher melting point because there's basically less distance between the positive nucleus and the delocalized electrons compared to sodium that's got a greater distance and more shielding between the positive nucleus and the outer electrons. So when you talk about these, okay, and you are comparing ionic radius, the larger the ion, the more shielding it's got. So just think along the lines of first ionization energy, the more shielding it's got, and therefore the weaker the attraction between that ion and the negative thing it's attracted to. In here, it's going to be a negative ion. In metals, it's obviously the delocalized electrons, okay? So that's what they do. You can either they can compare ionic and two ionic substances, or they compare two metal substances. What they can also do is give you an ionic substance and a metallic substance. And we're going to look at an example of a question like that further down the line, okay? But essentially, they will tell you which has got the higher melting point. And all you have to do is describe the bonding and then say, well, the electrostatic attractions in this must be greater than the electrostatic attractions in that because that one's got the highest melting and boiling point. That's all you need to do. I'm going to show you how to hack those as we move forwards. So here we go. We get into the fun stuff, all right? So simple covalent molecules. So simple covalent molecules, they can be, well, I'll go through the examples of what to expect with simple covalent molecules, but let's have a look. Generally speaking, hydrogen bonding is the strongest type of intermolecular force. permanent dipole next, and then induced dipole next. We will get to identifying, or talking about how to identify what type of bonding is, what type of intermolecular force is between different molecules. Okay, we'll talk about that. So hydrogen bonding, for example, ammonia, water, and hydrogen fluoride. Okay, they are the three big ones, if you like, because compounds must have a hydrogen atom directly bonded to a highly electronegative element, and they are NOF, nitrogen, oxygen, and fluorine. So your typical inorganic molecules that have hydrogen bonding are ammonia, where nitrogen is directly bonded to hydrogen, water, where it's oxygen, and then hydrogen fluoride, where it's fluorine. Okay, those are the only ones that you're going to come across really in inorganic chemistry. But of course, they can put bonding and relate it to organic questions, because all organic molecules are simple covalent molecules, aren't they? All right, methane, ethane, propane, butane, alcohols, aldehydes, ketones, like haloalkanes, you name it. So also, the only organic molecules you're going to come across that show hydrogen bonding between the molecules are alcohols, carboxylic acids, amines, and amides. Now, you don't come across amides year 12s. Don't worry about those for your exam at the end of the year. But alcohols, of course, contain an OH. Carboxylic acids also contain an OH. And amines, that's an amine, an NH2 on the end of a molecule there. Okay, so when it comes to organic chemistry, those are the three, if you're in year 12, but amides as well in year 13, that you need to say, okay, those are the ones that have hydrogen bonding between the molecules. And that also makes them more soluble in water. So my advice would be, if the question does talk about solubility, then ask yourself, does that organic molecule have hydrogen bonding? Look for an OH or an NH. If it does have it, then it's likely to be soluble. If it doesn't have it, it will not be soluble in water. So only these things, okay, and maybe not even amides, but only these things, I would say, are soluble in water to any extent. Okay, they're not all massively soluble, but they have to have that OH or NH to start with if you're going to stand a chance of them being soluble. Anything else, alkanes, alkenes, haloalkanes, aldehydes, ketones, not soluble in water, okay, because they don't have hydrogen bonding, because you need that hydrogen bonding to be strong enough to kind of get in between the water molecules, break up the attraction between the water molecules themselves, and kind of get dissolved. Next up, permanent dipole. Now, these molecules, these are kind of less strong than hydrogen bonding. These must be polar overall. Now, I know we can spot a polar bond where you have two elements directly bonded together, and if they're two different elements, you will have a dipole, okay? But you can't just look at individual bonds. You need to look at the molecule as a whole, all right? So is that molecule, I always think, right, is it, if it's asymmetrical, if it's not symmetrical, okay, then it's probably going to be permanent dipole, okay? Here's a hack for you though. Anything with a lone pair is likely to be or have a permanent dipole. So for example, like, I don't know, NCl3, okay, like that, nitrogen always has that little lone pair at the top. We'll talk about shapes of molecules and stuff later down the line, and that helps you kind of work with this. But if it's got a lone pair on the central atom, basically don't even question it. It's permanent dipole, okay? Every single time. And again, as I mentioned, anything that's asymmetrical in terms of polar bonds. So, for example, if we have methane, that I would say is symmetrical. Doesn't matter how you cut it, it's going to be symmetrical. Whereas as soon as you put like a chlorine on there, so like a haloalkane, okay, that's going to be delta positive, that's going to be delta negative. It's no longer completely symmetrical from any angle. You've got a negative end and a positive end, if you like, okay? If you think about this being the dividing line between one end and another, you've got a positive end and a negative end. So that's what you're looking out for. You're looking out for lone pairs, and you're looking out for an overall kind of what they call like a dipole moment. Okay, a dipole moment. So, oh, nice. RJ, is that helpful? Yeah. So, examples, PCl3, haloalkanes and carbonyls. What I mean by carbonyls is aldehydes and ketones. Some of you need to know about those in year 12, some of you don't, but just letting you know, okay? So permanent dipole, but you'll also find a permanent dipole in a carboxylic acid. So carboxylic acids are like proper double whammy. Oh, that's great, RJ, thank you. Proper double whammy. You've got a dipole here in your C double bond O, your carbonyl group, and you've got hydrogen bonding here. So, you know, they're pretty strong, the attractions between carboxylic acids. Now, the really fun bit. Induced dipole, aka van der Waals forces. Okay, van der Waals forces. Now, first statement is the most important one. And I don't know whether you knew this, been told this, realized this, but all simple covalent molecules have these. Okay, like in water, we say water's got hydrogen bonding. Yeah, it does. That's the strongest intermolecular force it has, but it's also got induced dipole forces. Okay, every single molecule to a certain extent has induced dipole forces. It's just that if there is another stronger intermolecular force that it has, we tend not to bother talking about the induced dipoles. Okay, so we're looking at if a molecule, any of those molecules with hydrogen are permanent, they've always got induced dipole as well. And that can be the difference if you can't tell what the difference is between two molecules. Okay, and I'll give you an example of that and what I mean. That doesn't make much sense right now, but I will promise. I promise I'll go through it. So all molecules have these. In fact, let's just talk about that very quickly now. I'm just going to go to this and I'll prove it to you. Okay, so all molecules have induced dipole forces. So if we take, let's say, methanol, for example, these, because there's an OH group there, because it's an alcohol, this is hydrogen bonding all the way, okay? And even, let's say, butane and butanol, okay, butan-1-ol, that's also hydrogen bonding. Now, if they asked you, okay, and just imagine there's, well, I'm just going to draw the hydrogens in. If they asked you, right, butanol has a higher boiling point than methanol. What we need to do is play a game of spot the difference. So we can say, well, both of them have hydrogen bonding. So hang on a minute, if they're both hydrogen bonding and they both have the same intermolecular forces, why does this one have a higher melting and boiling point? The reason is more carbons, RJ. Cloudy carbon length, absolutely. So yeah, this bit here, yeah, that's going to be hydrogen bonding with the molecules next door and this, that, and the other, and that's fine. But this non-polar section, okay, this non-polar section here, the forces that can be, the intermolecular forces that are created by these non-polar sections are, of course, induced dipole or van der Waals, whatever you want to call them, okay? So obviously, the greater the non-polar section in organic molecules, the stronger the induced dipole forces, okay? So it just goes to show you that most of the time, if you're comparing methanol to just plain old methane, yeah, spot the difference. That's hydrogen bonding. That's just van der Waals. We're away, okay? But of course, like I say, you just have to look at the molecules and play spot the difference, all right? Now, another example, okay, or the reason for that, and I want to tell you this, okay, and this is just nailed on every single time. The strength of these forces relates directly to the number of electrons within the molecule. The greater the number of electrons in a molecule, the greater the strength of the intermolecular force. If they ask you in an exam, why does ethane have a, let's go halogens. Why does iodine have a higher melting point than fluorine? Well, they've both got induced dipole forces between them. And you'd be tempted to say, well, iodine has got a greater relative molecular mass than fluorine. So that's why it's got stronger induced dipole forces between them, which is not wholly untrue because there is a relationship. The bigger the molecule, the greater the induced dipole forces between them. But that's not what really causes it, okay? What really causes it is because obviously if we have a greater relative molecular mass, then it's a bigger molecule. If it's a bigger molecule, it contains more electrons, okay? That is the thing they're looking for in the mark scheme, okay? That is the thing they're looking for. So if you find yourself saying iodine has a greater melting point than fluorine because it's got a greater MR, you're not going to get the mark for that. You're going to get it for saying the iodine molecule is larger and contains more electrons, which causes stronger induced dipole forces, okay? So yes, it's a bigger molecule, but make sure you mention electrons, folks, okay? Really, really important. So where you're going to find these, you'll find these, I'm using all sorts of different colors here. Group 8, even though they're monatomic, they're single atoms, you can actually liquefy them. So there must be forces between them. So group 8 also show induced dipole forces. You've got group 7 as well, which we mentioned. So molecular elements. So all your halogens, H2, N2, O2, P4 and S8. Okay, don't neglect those. Whoops. So phosphorus tends to hang around as P4, sulfur tends to hang around at S8, and of course, what you've got are your alkanes and alkenes. They're your typical non-polar organic molecules as well, okay? So just a little point here, the last little point about induced dipole forces, okay? Is this good for you guys? Actually, just checking in with you guys right now. I'm kind of rabbiting on here, but is this all good stuff for you is what I want to check. Before I go into the next bit. Brilliant. RJ, yeah, absolutely it is, because this is the most common topic from year 12 that comes up in A-level exams, okay, in year 13 exams. So that's why I'm doing these 3 sessions. So yeah, thank you, Alice. So as I say, okay, thank you, Scarlett. As I say, these induced dipole forces vary massively, okay? I would say you could even extend, there's such a range in obviously the size of molecules and stuff like that. Induced dipole forces can actually totally eclipse anything else that's had permanent dipole or hydrogen bonding. Let me give you an example of that. So this is a guide. Due to variation in strengths of each type of bonding IMF, they do overlap. For example, hydrogen fluoride, as we mentioned before, has hydrogen bonding between the molecules, has a boiling point fact of 20 degrees Celsius. However, iodine, I2, is non-polar and only has induced dipole forces, but its boiling point is 184 degrees, okay? So when you have questions and they're asking you, why does this thing have a greater melting point than that thing? And if the one with a higher melting point has got only induced, if it's non-polar and it's got induced dipole forces, that must just mean that molecule's so big and contains so many electrons that the induced dipole forces it has, like in iodine, must be stronger than the hydrogen bonding forces between molecules of hydrogen fluoride. So hydrogen fluoride, I mean, I've got a periodic table here. Hydrogen fluoride has got an MR of 20, and iodine has an MR of, quick maths, Rich, 300 and... hang on. It's not 300 at all. It's 254. Okay? So you can see that induced dipole forces, okay, it's not a hard and fast rule that if it's got hydrogen bonding, it must have a higher melting point than something that's non-polar. Not true, okay? But in those situations, in a question, you're not expected to know that, okay? You're not expected to know that iodine has got a higher melting point than hydrogen fluoride. But in a question, what they might do, and I've got an example of this, is give you two things. One's got hydrogen bonding, one's induced dipole forces only, but the melting points, like these two, are the opposite of what you'd expect, okay? But in that situation, that's all you have to do. That's got hydrogen bonding, which are pretty strong intermolecular forces, whereas iodine over here, whilst it's non-polar and only has induced dipole forces, it's got so many electrons, it's such a big molecule that those induced dipole forces must be stronger than the hydrogen bonding in this one over here. Okay, so you just let the question lead you. You're not expected to have this encyclopedic knowledge of all the melting and boiling points of all the molecules and elements in the entire universe. All right, so just let the question lead you and just go with it. And every single time, whichever's got the highest melting or boiling point, that means that's got the strongest bonds or the strongest intermolecular forces, depending on, of course, what you're dealing with. Now, the hack, ladies and gentlemen, the hack. And I don't like calling it a hack because to me it's just common sense. The question will guide you in terms of data. So, you know, unless it's really obvious, like we did before comparing ethanol and butanol, all right? Unless it's, well, I wouldn't call it obvious, but, you know, they'd ask you which has got a higher melting point. If there is a clear difference, remember, all we're doing is playing spot the difference here. They will guide you, okay? Like I've just said, they'll tell you that iodine's got a higher melting point than HF, all right? And then you just go with it. But what you need to do to answer these questions is A, describe the structure and bonding in the substances, okay? Half of the marks that you get, because it will always say, explain why this melting point and boiling point are different. And you just jump into an explanation. No, not everybody's missing marks, all right? You just sit and you just say, well, that's carbon dioxide and that's non-polar, so it's only got induced dipole forces. And that's magnesium. It's got metallic bonding. You know, it's got really strong electrostatic attractions between the ions and the delocalized electrons. Just describing it is half the marks. And once you describe the structure and bonding in each of those things, you can then relate those relative strengths to the melting and boiling points. That's the explain bit. So when questions say explain why, and it's got a difference in melting and boiling point, I'm not going to explain it. Okay, that is water. Okay, and that is, I don't know, sulfur dioxide. All right. You make a statement as to what type of bonding, and if they have intermolecular forces, just state what they are. You've got most of the marks. The last statement is, well, these are stronger than these ones, so it takes more energy to break them, and hence it's got a higher melting and boiling point. Okay. So that's it. Okay. The big thing that students always miss is this bit at the beginning, and you're not getting your marks for just describing the structure and bonding in those substances. Okay. So let me show you an example. Okay. Let me show you an example. Is it that one I want? Okay. Here we go. Table, this is a typical question. It's AQA, but it's completely relevant for everybody. Table 4 shows a melting point of 3 substances. We've got sodium chloride, we've got chlorine, we've got hydrogen chloride. Explain why the melting points of these substances are different. You should refer to the structure and bonding in each substance. Now, a lot of questions don't say that, but this is saying it, okay? So what we go with here, okay, yes, it is AQA, mate, sorry. What we go with here is literally just make statements about each one. I'd say that NaCl is ionic, okay? And, you know, we're describing ionic substances, so I'd say it's a regular lattice. So get your definitions down, guys. Regular lattice of alternating positive and negative ions, okay? With electrostatic attractions between them, okay? So that would be my kind of nailed on description of just what an ionic substance is, okay? Then you've got chlorine, okay? This is a non-polar molecule. It has to be non-polar because both elements are the same. You're not going to get a polar bond. And, you know, there's no difference in electronegativity. It is simple covalent or molecular covalent, whatever you want to call it. So, and it's so therefore, it's only got weak van der Waals forces or induced dipole forces between the molecules. Next up, HCl. Okay, HCl is a polar simple covalent. Okay, because there's a difference, delta, in electronegativity between the hydrogen and the chlorine, and you end up with a permanent dipole. Chlorine's more electronegative than hydrogen. Okay. Oh, thanks, Clyde. Yeah, sorry, you kind of just, yeah, thank you very much. So you're getting ahead of me, and I'm just too busy kind of doing this myself. Now, of these 6 marks, ladies and gentlemen, you've probably got already in the bag about 4 of them. Okay? So obviously what we need to do here is now look at the relative melting and boiling points. So I would say NaCl highest as the electrostatic attractions between Na plus and Cl minus are stronger than the ID forces in Cl2 and the permanent dipole forces between HCl. Okay, so you're just going boom. Sodium chloride is the highest. Why? Because those attractions must be stronger than the other two. It's all relative, okay? And they've given you the data, so you just say it. Just say it, okay? Now, what do we notice here, guys? Chlorine is non-polar, okay? Hydrogen chloride is permanent dipole, okay? So this is one of those situations where you're like, hang on a minute, hydrogen chloride's polar, but wait, why has it got a lower melting point than chlorine? That doesn't make sense, because I've got in my brain that polar molecules have stronger intermolecular forces than non-polar molecules. This is where we need to say, you know, although or despite the fact Cl2 is non-polar and has van der Waals forces between them, it contains a large number of electrons. Heck, you could even state the number of electrons it's got, because you know the atomic number of chlorine, which is 17, so you could say there's 34, okay, in a chlorine molecule. So what that means is, therefore, these van der Waals forces are stronger than the permanent dipole forces in HCl, okay, and that's only got 18 electrons in it, okay, but even though it's polar, it must be weaker than Cl2, because Cl2's just got a truckload of electrons in it because it's just massive, okay? So again, this is what I mean by trust the data. Just go with it, okay? So what I want you to do is have a more fluid view of the relative strengths of these intermolecular forces, okay? Especially, I mean, if it's just permanent dipole versus hydrogen bonding all the way, okay? Hydrogen bonding all the way. And if the molecules are about the same mass, okay? But where you've got these non-polar ones, where you've got these ones that only have induced dipole forces between them, be prepared to say, well, actually, that molecule's massive and it's got loads of electrons. So those those induced dipole forces must be like just ridiculously strong, okay? And stronger than the permanent dipole in another. So are we on board with this, guys? Give me a kind of score out of 10 with kind of how much more clarity you've got on these sorts of questions. Describe the structure and bonding in the things, then just talk about the relative strengths. That's all you need to do. And like I said, you're guided in the question as to which is which. Wonderful. Thank you, Cloudy. Thank you, RJ. That's a big number. Thank you, Alma. Brilliant, Alice. Thank you. So if any of you are year 13 and you want some more of this, obviously I'm doing this next week during half term. There's 10 hours. So 2.5 hours each day. Basically, I'm just kind of hijacking your revision for those days for chemistry. Exam training like this. This is the stuff we're doing, okay? This is the stuff we're doing. So if you want to join me next week, you know, I can give you the link. Actually, I will put the link in here now. Just shameless kind of, you know, not not selling, I'm kind of advertising what I'm doing next week. And boom, there it is. It isn't for free, okay? I'm kind of, putting, so I always try and put as much love in the world as I can. But equally, I need to pay for the electricity. So, all right. So that's intermolecular forces, and it goes for any sort of question. Think, right, let's play a game of spot the difference. All right. That's what we're looking to do, is play a game of spot the difference when it comes to bonding questions. All right. And when you're looking to identify the whether a molecule is polar or not, or non-polar, part of that comes down to your VSEPR, okay, your shapes of molecules. Now, there are a couple of things you need to be able to do here. There's one thing you need to know, but a couple of things you need to be able to do, okay? So, RJ, are you already signed up? Shapes of molecules. Okay, this, ladies and gentlemen, is your definitive list of shapes and bond angles that you need to know. All right, so let's just go back here. Ooh, right, okay. So what I've done here, I think it's easier to think of them this way. At the top half, okay, at the top half of that, these are all molecules that contain no lone pairs, okay? Well, maybe ask, RJ, rather than tell. That might be a bit more tactful. And obviously, if you found this useful, then yeah, it's definitely going to help. And I can't guarantee you're going to, it depends where you're starting. But, a lot of the time, and I've got 20 years experience of this, right? A lot of the time, students are smashing the books, smashing like the mind maps and the flashcards and highlighting and rewriting notes and revising. It's like, I'm not ready to do papers yet. Let me just have a little rant here for a second. Well, RJ is perfect for that. I'm not just saying that, it is perfect for that. Because most of the time when students kind of hit a glass ceiling, and I'm sure you've all been there, like, why? I just know my stuff, I know all this, but I'm just not seeing a grade improvement. And it's a lot of the time, it's down to exam technique. It's down to not doing enough questions. It's down to not practicing enough and seeing the pattern in which questions come up, and knowing how to answer specific types of questions. Like maybe you've seen in my TikTok, guys, I've got 3 types of buffer questions on there, those of you doing A-level. And before I told anybody that, everyone was like, really? There's only 3 types and you have to know 3 types. Well, yeah, because I've done the analysis, and basically for every exam board, there's only ever 3 different types of buffer questions, and you're going to get one of them. So if you can recognize that one, then you're in, okay? So, where was I? Oh, yes. So, shapes of molecules. Sorry, just a bit of a rant there. I think it's easier to think about the ones that don't have lone pairs and then the ones that do have lone pairs, okay? So these are the ones, I'm not going to run through all of these in great detail because you just need to learn them, okay? So you've got linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. They're your main shapes. If you're looking at T-shaped and seesaw and all that jazz, just forget about it. You don't need that stuff for any exam board, okay, folks? I promise you that. Like I said, 20 years down the line, and you don't need that anymore. You used to, but not now. So, facts. You need to know the shape, how to draw it 3-dimensionally, the number of bonding pairs and lone pairs around that central atom, and of course, the bond angle or bond angles of them. Okay, that is factual recall. That is where your revision is going to help in terms of flashcards and stuff like that. Okay, what it doesn't do is tell you how to spot what shape a molecule is, and that's what I'm going to spend the next 10 minutes or so going through with you. Obviously, we've got our lone pair ones. These ones, if they're this shape, okay, they've got a lone pair. Oops, I didn't mean to rub that out. Didn't know I could rub that out. If they've got a lone pair, what do we say the IMFs between them are? If they've got a lone pair, essentially. What are the intermolecular forces between molecules that have a lone pair, generally speaking? Thank you, Cloudy. Permanent dipole. Permanent dipole. Unless, of course, this happens to be water. And, of course, it's going to be hydrogen bonding, isn't it? You just need to spot that. But if it's not hydrogen bonding and it's got lone pairs, then it's going to be permanent dipole. Okay, permanent dipole. So those are the ones you need to learn. Now, in questions like this one. 8.3, and again, it's AQA, but it doesn't matter. Okay, I just pulled these because they're relevant for everybody. Draw the shape of a POCl3 molecule and the shape of a ClF4- ion. Include any lone pairs of electrons that influence the shapes. In a POCl3, the oxygen atom is attached to the phosphorus by a double bond. So they're actually helping you a little bit here, and uses 2 electrons from phosphorus. Name each shape, suggest the bond angle for the ClF4, and that's it. So, where you stand at the moment, before I run through these guys, how confident would you be at getting 5 out of 5? How many marks do you reckon you'd get out of this before I kind of go through it with you? Give me a mark out of 5 and think, I'd smash this 5 out of 5, or actually, I'd just be guessing, like, is that -5, RJ? All right. I mean, and that's not possible, but maybe that's kind of what's the opposite of knowing something? Kind of not knowing something, but then what's worse than not knowing something? I don't know. Okay, 2 out of 3, Scarlett, maybe 3, Cloudy. Okay, so how to do this? In any molecule, okay, you will have a central atom. And in this one, it's pretty clear what it is. It's going to be that chlorine that's the central atom here, okay? Yeah, don't worry. Actually, hopefully by the time I'm finished, RJ, you'll be like, easy marks, all right? So first of all, look for the central atom. Then, what group is it in? Because GCSE, folks, if it's in group 7, it's got 7 outer electrons. If it's in group 5, it's got 5, all right? So you're always going to be dealing with your P block elements over on the right-hand side because, of course, if it was a metal, then it would either be a salt or metallic. So, you're always going to be dealing with groups on the right-hand side of the periodic table. Now, they've told us, obviously, that in the POCl3, because it could either be phosphorus or oxygen in this one, couldn't it? Because there's only one of each of those. So it's like, which one is it? But they've told us in POCl3, the molecule of, the oxygen atom is attached to phosphorus by a double bond that uses 2 electrons from phosphorus. So phosphorus is our central atom here. So phosphorus, let's draw that. In fact, let's do a circle. I've got a circle to do, Hickey. Okay, so it's black, but that doesn't matter. Let's do it that way. There we go. Okay, so phosphorus in the middle, and we've got 1, 2, because it's in group 5, 3, 4, 5. Okay. Now, I've done 2 at the top. Now, the reason I've done 2 at the top is because they've told me that it makes a double bond with oxygen. Okay, so I'm just going to put oxygen in here. This one, no fill. There we go. Okay, so that's our oxygen. That's a double bond. So it's got 1, 2 electrons from oxygen there, and of course we've got the other 4. Okay. Now, of course, what makes sense is we've got 3 chlorines bonded around this phosphorus as well. Oh, look, we've actually got 3 electrons that we can use to make those covalent bonds. Okay. So what you do is you then add your satellite, I call them, atoms. Okay, so we've got 1 chlorine there, 1 chlorine there, and 1 chlorine there. All right, so in another way of looking at it, we've got P double bond O, single bond chlorine, single bond chlorine, single bond chlorine. Now, one thing to remember in VSEPR, shapes of molecules, ladies and gentlemen, is that a double bond basically just acts like a regular single covalent bond, okay? So just treat it like another single bond pair. I know there's 2 pairs of electrons in there, but when you get a double bond, just go with it. It is just treated as another bonding pair. So what shape is this when it's at home, ladies and gents? It's got no lone pairs because we've used all the electrons up. and it's got 4 bonding pairs. Tetrahedral, boom. Okay, so that is tetrahedral. Okay, so that's that bit nailed. All right, 2 out of the 5 marks in the bag. So like I say, there's a pattern to these. You put your central atom, put your electrons around it. You might need to do it in pencil, okay, because you might not put the electrons in the right place to start with, but that's absolutely fine. You can rub them out and do it again, okay? Maybe even do it on a separate bit of the paper in the exam, and then when you're happy with your answer, pop it on the page, all right? No harm in that. Now, CLF4. So we have got, let's do this one. So CLF4, so we've got a chlorine in the middle, like so. We know it's in group 7, so 1, 2, 3, 4, 5, 6, 7. Now, how the heck do we get 4 fluorines around this? How do we get 4 fluorines around this? Well, what you got to remember is that if I just go here, and it's not talked about a lot in a lot of specs, but it's a fact. Where you have kind of these molecules here, or these elements here, sorry, what they can do is what's known as expand their octet. Now, what does that mean? It means actually they've got access. So phosphorus, in fact, let's just get rid of that. Phosphorus, sulfur, and chlorine, they're pretty close, you know, like they're kind of 3p whatever. They're not very far from the 3d orbitals that are being used for transition metals. So there's empty d orbitals knocking around. So they can make use of those empty d orbitals. You'll never be asked to explain this. I'm just giving you a reason, because every time you have a reason for knowing something and an explanation, you're more likely to remember it, right? So P, S, and Cl, they can all use like 3d orbitals, whereas arsenic, selenium, and bromine have access to these ones. So what these can do is expand their octet and have more than 8 electrons in their outer kind of energy level that they're using for bonding. We're used to seeing 8 all the time, aren't we? But what these guys can do is expand the octet. So that's how we can end up with PCl5, for example, which has 12 electrons in the outer energy level, and SF6 that also has 12 electrons in the outer energy level. So it's okay to use more electrons, okay? And that's how we end up with these larger bonding types over here, okay? Trigonal, bipyramidal, and octahedral. So where do we put these fluorines in? Well, let's just start banging them in, shall we? So I know I've got 7 electrons in total around chlorine. Let's rewrite this. So let's just put a fluorine here that's making a covalent bond, a fluorine here that's making a covalent bond, a fluorine here that's making a covalent bond. Okay, the question is, where does that come from? Where does that charge come from? Now, the answer is always one of the satellite atoms. All of these fluorines came in just as regular old fluorine, okay? 3 of them, okay? And they make the single covalent bond as you'd expect a halogen to do with the chlorine. But one of them must have been carrying a negative charge with it. In other words, this fluorine here, the 4th fluorine, must have an extra electron already and then bond to the chlorine coordinately, so like oddative covalent bond, okay? Now, I know that, because, right, first of all, anything that's got a charge on in terms of a molecule and the shape of a molecule, that charge comes with one of the satellite atoms that are going around it, okay? In this case, it's an F-. And because this has already got a full outer energy level of electrons, it must be that it's using that outer energy level, it's using those 2 electrons to form a bond with chlorine, like so, okay? So that's what we've got there. We've got like this creepy, weird little dative covalent thing going on, and that just gives the whole molecule a negative charge now. Okay, I'll give you another example of that in a second. I'll just finish this off. So for chlorine, if we zoom in, we have got, of chlorine's electrons, we're using, let's use a different color actually to highlight those. So we've got 1, 2, 3 being used. 3 of them being used, okay? The other 4 must be here like so, okay? The other 4 must be here like so. So the question is, what's the shape? Answers in the chat for me, please, guys. Answers in the chat. What is the shape? It's got 2 bonding pairs and 4 bonding pairs and 2 lone pairs. Have a look at that data sheet I gave you before if you can't remember. It's not trigonal. Trigonal is tri, so you'd think there's 3 bonding pairs. Anything with tri is 3, and there's more than 3 bonding pairs here. Alice, top marks. It is square planar. Okay, so that's a square planar molecule. And what actually it looks like is, I won't draw it because it's here. You get the lone pair above and below. So it's square and it's planar because all of these bonds are on the plane, and you get the lone pairs above and below. Okay, so that's why that's square planar. The bond angle here is 90 degrees, and that's just recall. But obviously figuring out these in the first place, that's the trick. All right, that's the trick. What time are we on? Right, let me give you one more example real quick of like an ionic shape. So for example, NH3, that is trigonal pyramidal, okay? Because the lone pair has got greater repulsion than the bonding pairs. This is a 107 degree bond angle. Now, if we look at something very similar, which is the ammonium ion, okay, like so. Ammonium is NH4+. And if they ask you, what's the shape of NH4+? Well, actually, like I said, if it's got a charge in it, that charge must have come with one of the satellite atoms. We know we've got a lone pair up here on nitrogen. And if a H+, because literally that's the difference between NH3 and NH4+, isn't it? A H+. That's the difference. That H+ comes in and it forms a coordinate bond with that. And now it's tetrahedral and it's got a full positive charge, and the bond angle is 109.5. So, you know, that's the difference between those two. Okay, so you can see how if it's got a charge on it, it came with one of those satellite atoms that came with it. This is not something that is going to click overnight. Okay, it does take practice. It takes time. It takes seeing the different examples in the exam papers. It takes, it takes mistakes to learn from. Okay, I say it with year 13s. I say it with HNMR all the time as well. Right? You can read all you want about HNMR, but until you start smashing the questions and making mistakes and learning from them, you're not going to get any better at it. Okay, so it's just one of those things. The VSEPR, shapes of molecules, bonding questions. Okay, so hopefully now you know how we can actually kind of go about these questions and how to attack them. Okay, so the big messages are, yes, know your relative strengths of your different types of bonding. All right, but be prepared to compare. Let me just show you another question here actually very quickly. This was his first question. Be prepared to compare different types of bonding. So why does sodium bromide? Oh, yes, I haven't shared those questions, have I? I do apologize. They've got the mark scheme on as well. There you go, Alice. So this one here, use your knowledge of structure and bonding to explain why sodium bromide, NaBr, has a melting point that's higher than sodium and higher than that of sodium iodide. Okay, so here you're comparing sodium bromide with sodium, right? That's half the marks, okay? And then comparing sodium bromide with sodium iodide. And that's what I was talking about with you comparing two ionic substances here. So this is ionic versus metallic, and then you're comparing ionic versus ionic. So you, again, play a game of spot the difference. But as I say, apologies, half the marks are, okay, what's the bonding in sodium bromide? What's the bonding in sodium? What's the bonding in sodium iodide? And then you can start comparing, okay? And that's how you get the marks, folks, all right? Oof. That is Bang on an hour. I am very impressed with myself. Got my timings right. Okay. So you've got those cheat sheets. You've got some questions. Okay. Hajar, is this available? What do you mean by that, matey? Is this available? Am I available? Sorry. So these questions I've just given to you. Okay. Oh, is this AQA? Okay. Yes, it was an AQA question, that one. All the questions we've looked at tonight were AQA ones, but they're totally relevant for everybody. Okay. I only ever use questions that are curated and relevant for everybody. Okay. My general advice is if you want more questions, anything with calculations involved, you're pretty safe. Okay. So whether it's Gibbs, whether it's Arrhenius, whether it's rates, well, whether it's pH, whatever, that's fine. Steer clear of other exam board organic questions. Okay, steer clear. Now, next week, I'm not going to be running any free sessions next week. This was just kind of like a little taster session, a little moose bouche as to what's happening next week. Okay. So next week, as I say, it's focused completely on year 13. We've got 4 days, 2.5 hours each day with a break in the middle. So it's 10 hours of tuition. And if you sign up, you'll get to come and see me for an hour the night before each exam, just to kind of blow the cobwebs away, kind of get rid of any kind of fears or kind of anxieties you have. I'm going to coach you right the way through your exam. So if you sign up for those tutorials next week, that's what you'll get as well. So it's basically 13 hours of tuition. There's still spaces, so if you want to sign up, the link's in the chat. Equally, if you go over to the Chemistry Coach website, it's just chemistrycoach.co.uk, and go to live group coaching or live coaching, then it's at the bottom of the page and you can sign up there. Equally, if you're on TikTok, there's a link in TikTok which will take you straight through to the registration page as well. All the details of everything that I'm covering are here, guys. Okay, I'll just share that again for you. There. Okay, so if you want to click on that, if you're wondering about next week, like all the details in detail as to what I'm covering are there next week, and I'll be giving you question packs, cheat sheets. If you look, I did an organic one for AS on Tuesday. Okay, we did organic on YouTube. So if you're AS and you want the organic version of my organic reaction tracker, then you can go and download that for nothing. If you want the year 13 version, that's what I'll be giving away next week. Okay, so yeah, if you want to join me for exam training, please do. If you know anybody that might be interested in it as well, please share the love. Zakira, so do you think you can get full marks in A-level chemistry if you done if I did it this year? If I did it this year, I'm always wary about that, actually. That's a very interesting question. Would I get full marks? That's my pleasure, guys. Thank you. I really appreciate you coming along to this. And I'm just really pleased you've learned something from it as well. And if I've gained you an extra 2 or 3 marks in your exam, then I've won. Okay, you've won. So do I think I get full marks in A-level chemistry exam? I will never say yes. The reason being, the different exam boards have always put kind of like some naughty questions in there, okay? Either through just strange comprehension, the way they word the questions, or if it's AQA every year, somewhere in the paper 1, paper 2, or paper 3, just put a ridiculous kind of mathematical numeracy problem-solving question in there. And I'll be honest, my maths in terms of the spheres of A-level chemistry, I've got hacks and cheats and stuff like that. It's just, they're all really reliable. As soon as I come out of that comfort zone, I'll be honest, I'm not an amazing mathematician. So I'll never say, yes, I'll always get full marks, but I guarantee you will always be in the mid to high 90s. And because I sit them every year, not like officially in an exam room with students, but once I can get hold of them, I just sit and I do them. Because the best way I learn about what the exam boards are thinking and how they do their questioning is not just by sitting and looking at a mark scheme. I literally sit and do that exam in a timed exam condition myself, okay? So that's how I go about it, and that's how I see the patterns and stuff and trends and what have you. Will I come out with predicted papers? Can I just go on my kind of soapbox again here, folks, just for a second? I hate predicted papers because that suggests that people know what are going to come up in the exams. That can't be true unless they wrote the exam and then they're not allowed to do stuff like predicted papers or even tutor. If you're an exam writer, you're not even allowed to tutor because there's always that element of kind of, bias towards the things that are going to come up in the exam. So anybody that releases a predicted paper, they're not. They're not, okay? Which is why I never do them. The reason being, they're not predicted. They're just based on exams that have been. Because all we know about what is included in paper 1 and paper 2 and paper 3 is what's happened. Now, there is some repetition, okay? I can guarantee you that there will be an Arrhenius question in your A-level exams this year, okay? Because it's in every year, all right? And it's new for this specification. So they always put, even if it's a small one, it's going to be in there. So we can only look at, and there's no patterns or trends, all right? I like to think of it like flipping a coin. Just because you got heads 5 times in a row, does that mean it's more likely you'll get a head on the 6th, or does it mean it's more likely you're going to get a tail? It's a bit of a mugs game, to be honest with you, predicted papers. My advice would be, okay, I've analysed the papers. I know what comes up every year. I know what tends to carry a lot of marks compared to other things. So it's all based on statistics. I wouldn't like to then go ahead and predict what is going to come up in your exam because I'd end up with egg on my face. You'd be annoyed because I told you to revise this and not that. So my advice would be do every single past paper. There is no better practice or predictor for what you're going to come across in your actual exam than sitting the past exams that already exist. The other reason is that anybody who's not officially kind of trained in terms of building exam papers and putting them together is never going to get the balance that you'd expect in an actual exam in terms of how many marks for bonding questions, how many marks for enthalpy questions, how many marks for calculation questions, how many marks for kind of explain questions or deduce questions and things like that. They're never going to get the right balance, which is why your tests in school and stuff are always a little bit different to an actual exam. So there is no better practice and you cannot better prepare than just by doing the past exam papers. Okay, the past exam papers are the best practice in timed exam conditions. Don't fool yourself by sitting with your phone on the side or kind of notes in front of you and don't start a timer. Start a timer. Put yourself under pressure, folks, okay? That will be my advice. And I apologize for jumping on the soapbox there. I'm surprised you're still here. But that would be my advice. People sell predicted papers. I think that's really naughty. They're not examiners. They don't have the insights necessarily to kind of really put a balanced paper. It'll be close, but they're not the real thing. Use the real thing for practicing papers, guys, is my best advice for you. Is that okay? I'm going to shut up now. So, final word. If you don't follow me on TikTok, follow me on TikTok. Yeah, that's where I spend most of my time in terms of putting like little videos and stuff out. If you haven't seen my profile, then you can scroll through. It's all pretty clearly labeled as to what it is each video is on about. So there's some real handy hints and tips and stuff in there. If you haven't looked in it, if you're A-level, go and check out the Buffers one. So that's my pleasure, folks. I enjoy these sessions. It's fantastic. So you know what? Any AS students, I'll be doing the same again next year. We're on a rolling basis. Like I said, I always try to put a bit of love and a bit of good karma out in the world for students. But equally, if you like it, then I'm always available for one-to-one tuition and these group sessions like I'm doing in May half term. So yeah, keep an eye out, guys. If you're AS for next year, if you're A-level, then that's what I'm doing next week. Like I said, I'll coach you right the way through your exams as well. We can get our heads together the night before each exam, and we can calm nerves. I can massage each other's egos. Whatever needs to be done, that's what we'll do. Okay, so thank you so much, guys. If I don't hear from you before any exams that you're having this year, whether they be internal at AS or external for A-level, all the very best, folks. Okay, and just remember, it's about what you can do, not what you know in chemistry. So practice those papers, get those papers under your belt. The more practice you get, the better you will be at answering those questions. All right. So I'll see you around, folks, and take it easy and all the best for this summer.